So in this video we are going to show how you can model a cylindrical water tank using StartPro, and then to check the effect of temperature difference um, on the walls of the tank. So we've launched the StartPro interface. Check the space option and we give it a name. Then we need to run the structure wizard to obtain the cylindrical shell of the tank. And wait for it to come up. Select surface, apply models, select the cylindrical surface, and this comes up. These are the details of the tank we want to model. The height of the tank 2.5 meters, and then the diameter of the tank 3.38. So let the length be 2.5, which means that the start radius will be 1.69, and then the end radius will be 1.69. Let this be 1 and let this be 0, and let the number of divisions along the length be, let's increase it to 8, and then let the number of divisions be 36. Then we say apply. This is the shell of the tank that we've modeled, and then we can transfer this to the StartPro interface, and then at point 0, this is the shell of the tank that we are interested in, and we can confirm that the diameter of the tank is 3.38 meters. Having done that, we need to quickly get the support beams and the columns, since the tank is an elevated one. So we'll go to command, go to geometry, we run another structure wizard, and this time around we go to frame models, circular beams, and let the radius be 1.69, and let the number of bays be 18. We say apply. So this kind of ring beam comes up, and then we are going to transfer it to the model also. And now let the point be 0, 0. Then as such, you can see that the beam has been connected to the base of the tank. So we can get the columns turned this way. We can highlight the entire nodes. Then we can go to view, and we say view selected objects only. We can turn it to plan view. Okay, So we need to mark out the location of our columns. Remember that the we have a total of 36 divisions for this particular tank model. So which means we need to um, we are thinking of having 6 columns to support the tank. So let this be 1, 2, 3. Let this be 1, 2, 3. Let this be the first location. 1, 2, 3. So that the total 1, 2, 3, 4, 5, 6. So let this be 1, 2, 3. This should be able to give us exactly what we are looking for. So we can highlight the nodes that we are interested in. This is 1, this is 2, um 3, 4, 5, and 6. So we can say copy, paste. We are going in the negative y direction. We can say -3. We say okay. If we turn around to this view, we can use geometry to connect beams along the y-axis. So we've been able to form the columns and the ring beams. So if you look at the entire geometry, for now we have something like this. Alright, so we can go ahead to model the base of the tank and the top, since we are assuming that the the tank is not open at the bottom and at the top. We can also go to view selected objects only, go back to plan view, and we can generate surface meshing as usual. So let the number of divisions along each length, keep it as 2. Then we say okay. We've been able to form the bottom slab of the tank. We are going to disregard the openings at the top and model the tank um, as completely closed. We can just repeat the process. We can as well copy and paste depending on what works. So okay. Okay, we've been able to model the tank exactly the way we want. Then we go over to general. We can define the properties. We have a 300 column. Then we have a rectangular perimeter beam of depth 0.5 meters, and the width is 0.3. We can add, and then the thickness of all the plate elements is 0.25. We can add, then we can change the view of the structure and assign the columns. We can then assign the beams, and then assign the plate thickness properties. Then we can define the support conditions. We can create, we are assuming fixed supports all the way. We assign the supports. So we've been able to get this done, and the 3D view of the structure is something like this. You can look at the 3D configuration. This is what we have in 3D to represent the tank. The shell of the tank is supported on the ring beams that are going all the way. The tank is, there is a top slab, and just like I said earlier, we have disregarded the openings. So having done this, we can go straight away to define the loads. We are now going to consider pressure load on this on the walls of the tank. So let us add load case 1. We can give it a name, and then we are going to add temperature loads. Now the temperature change for axial elongation is just like the average temperature, and it is given by the inside temperature. We've taken it as 120 degrees Celsius, and then the outside temperature, we've taken it as 25 degrees. So the average will be 25 plus 120 divided by 2, which is giving us 72.5. And then the temperature difference will be 25 minus 120, which is giving us minus 95 degrees Celsius. Now the temperature differential from side to side applies to beams and columns, doesn't apply to plate elements. So we are going to apply this temperature load to the shells of the tank only. So we pick this, apply, you can say assign to selected beams and plates, and we assign. So this is the temperature load on the shell of the tank. We need to go and make sure that the parameters we are dealing with are consistent with the data we need for the analysis. You can check the modulus of elasticity and then the coefficient of expansion of concrete. So this is the stored input editor. Can go to materials, let's change the modulus of elasticity to 2.8, and now the Poisson ratio of 0.2, and this is consistent with what we need to have. Okay, so having changed, let's change the density to 25, so we can close. Okay, so for us to do the analysis, say all, we add cost points and analysis results, we close, and then we can run the analysis. Always remember to visit www.stradford.com for all advanced civil engineering analysis and designs. You can also contact us for structural design and detailing. So the results are ready for the temperature action. You can view the displacements in the tank as a result of the temperature load. You can actually see the increase or the bowing of the tank shell as a result of the temperature inside the tank being higher than the temperature in the surrounding of the tank. Quickly, we can go to the beams just to check the effect of temperature on the columns. When we pick one column, we have negligible axial stresses and bending moment on the column due to temperature difference, which is expected. Then we also have some bending moments but high axial stresses. We have high axial forces in the ring beams, which we think is reasonable given the deformation profile of the tank, and this shows that the ring beams are in tension with axial forces in magnitude of 2315 kilonewton. Okay, we can go over to the plates to see what is going on. We can check the bending moments. Okay, we may have to adjust our view a little bit Let this represent a section of the base, and let this represent a section of the tank. We can say view selected objects only. With this, we'll be able to see what's going on. These are the bending moments in the tank shells, and we can also view the bending moment in the y direction. Right, 319, which we expect. This is the torsion, the twisting moment due to temperature difference. We have the maximum at 102 and then the minimum at 88.4. Then these are the shear forces, and then these are the axial forces, having very high magnitude of axial forces in the tank. So you can go through by the time you model yours, and then check all the internal forces that are induced in the tank due to temperature difference. Thank you for watching, and remember to subscribe to our channel for more videos and tutorials. Thank you.